Welcome on the Promax webinar focusing on capturing CO2 from syngas. So we will be focusing on syngas. We will describe what it is, why it is produced, and we will have a look also on the syngas market, current and also on the predictions for the future. Then we will have a look on choosing the right CO2 removal process for our stream. And then one by one, we will introduce chemical absorption with amines, chemical absorption with hot potassium, then also physical absorption, membrane technologies, and low temperature distillation. I will show you also the models. So we will have also theoretical introduction, and then we will have a look inside the models, how it can be modeled, and which features you can use in modeling these technologies. So first, let's start to define what the syngas is. So syngas or synthetic gas is a gas mixture containing carbon monoxide and hydrogen. It may contain also other components such as carbon dioxide, methane, nitrogen, water, or other hydrocarbons with condensable compounds. Syngas is formed when carbon-rich feedstock is put in high heat, high pressure, and oxygen deficient conditions. Based on the feedstock which is used, the concentration of the mentioned components may vary. On this picture or the table, you can see what are the usual values or what are the borders where the values are moving in volume percent of the certain species, of the concentration of the species. And I mentioned the feedstocks, and the traditional feedstocks are made of natural gas or coal. And as gasification technology has developed, additional feedstocks such as biomass have come into use as well. Now let's answer the question why we produce syngas. So syngas is an essential feedstock for hydrogen production. Also, it's a raw material used to produce several chemicals such as ammonia or methanol or synthetic fuels, Fischer-Tropsch. Ammonia produced from the nitrogen and hydrogen in syngas is essential for fertilizer production, which supports agricultural productivity. Similarly, methanol derived from syngas is crucial for manufacturing formaldehyde and also plastics and adhesives. And all this drives the syngas demand even further. Here you can see the main key producers of syngas currently, all the companies. And in the year 2024, the global syngas market reached 260 million normal cubic meters per hour, with an estimated value of nearly $57 billion. So the market is therefore very large, and its further growth is being driven by concerns over the availability of traditional energy sources and efforts to regulate greenhouse gas emissions or the expansion of industrial gasification. And you can have a look on this picture. Probably this picture is the reason why we are all here together. We can see the consumption or the production of syngas in the year 2024. And on the right side, you can see the predictions for the year 2033, which is in, let's say, 10 years almost. And the production of syngas will be almost doubled. So new technologies will need to build up also with the all CO2 capturing technologies. So this is probably the reason why we are here today. Now let's have a look at the model of the syngas production. And there are several ways how to produce syngas. We can produce it by steam methane reforming, partial oxidation, autothermal reforming, also the combination of some of the technologies, or gasification. And since the steam methane reforming is the most widely used technology for both syngas and hydrogen production, we will have a look at this type in this flow sheet. So steam methane reforming. And as we can see, the model, we have steam stream and natural gas stream. We're mixing it together and send it to the reformer. Inside the reformer, there is occurring this first reaction. So methane is reacting with steam and forming carbon monoxide with hydrogen. There is also occurring the second reaction where methane is reacting with steam again and creating carbon directly, the carbon. Both reactions are endothermic, so we need to supply heat to the reformer. That's why we have also this second line here. So we are mixing air with fuel gas, burn it, and we are using the heat to increase the temperature in reformer, and then to preheat the feed stream to the reactor. To the technology, also the catalyst is sensitive to H2S, so any significant sulfur in the natural gas must be removed in a desulfurization unit before the SMR. And if the feed is containing ethane or heavier hydrocarbons, a pre-reformer can be installed upstream of the main reformer. That was the technology overview. Now let's have a look at which property package we used. I will go to active environment, where the new window pop up. Here I can see all the components I added to the environment. And if I will go to the property package, I can see that for this model, I use Tank Robinson. When I do right click and click on what's this, I can see the short note, which property package I can use for which process. And if I will go back and press F1 button on my keyboard, it will directly connect me with the Chromax help, where I can go to physical property package applications, where is the table with all the property packages with their applications, also some nodes, and we are using Tank Robinson, so I can open it. And if you will be interested, you can also read slightly more information about this property package. I'm going to close the window. Also this second one. And besides the basic blocks as heat exchangers or valves, we have the reactor in here. I'm going to open the reactor. I will go to process data, and we can see that this reactor is modeled as Gibbs minimization reactor. If I will go to the components, I see that all components is reacting. And in this reactor, it's possible to set also the constraints. So for example, let's say certain components reacts only over 500 degrees C, then I can put the constraint in here. We don't have anything like this in this case, so no constraints are there. But why I show it to you, the Gibbs minimization is the fastest and simplest reactor in Promax. It's very easy to set it up, and it basically takes all the inlets, find the Gibbs minimization of all the components going in. That's why I showed you the components, check the constraints if there are any, and then find the minimum Gibbs energy in the set of the products and create products afterwards. So that's the Gibbs minimization reactor. Now I can open the stream. We can see the composition of the stream. And since we want to maximize the hydrogen yield, here's the hydrogen. After reforming, the produced carbon monoxide is typically reacted with remaining steam in our stream to produce CO2 and additional hydrogen. And this takes place in the water gas shift reaction. That's why I'm going to send this stream via cross flowsheet connector to another flowsheet. So that's the same stream. We are sending it from steam methane reforming flowsheet to this water gas shift flowsheet. The water gas shift reaction, it's right here, is equilibrium limited and it's slightly exothermic. This reaction is often conducted in at least two stages, where first stage is a high temperature step. It's taking place from 350 to 450 degrees C at iron-based catalyst. And this first high temperature reaction is the fast reaction, which is there favored. And then we have the low temperature step, which taking place from 200 to 250 degrees C. And usually it's a copper-based catalyst. And this step is high conversion step. Now we can have a look in thermodynamic package again. We have anything new in here, so we still can use Bank-Robinson, or we are still using Bank-Robinson. We have also reactors here, so I'm going to open it, go to process data, and last time we had Gibbs minimization, so we had this one, but in this case, we have equilibrium reactor. In this case, we also need to specify the reaction set. So we are not using Gibbs minimization anymore, so we are using more advanced reactor types. And then that's why we need to specify also our reaction. So the reaction is specified in here. If I will go to the equilibrium, the data for the equilibrium reaction is specified here. So this is more advanced reactor, and you have even more options from which you can select. As I mentioned, this is just brief introduction. If you will be interested how to specify the reactor inside Promax, we have the YouTube video, or you can check also the help, and there it is described step by step how you can do it. And again, please remember that anything you do in Promax, you can anytime reach out to us. All right, so we are sending the stream from steam methane reformer, as I said, and it goes to the set of two reactors, and we can check our outlet stream. So I'm going to open it. And in this right side, there is a picture of the different types of technologies and what are the usual concentrations of certain species used. We used SMR with water gas shift, so these are the usual concentrations. We can then compare it, and these are two different other technologies. And our product stream, in this case, has 48 degrees C. It has 380 psi, but let's see in bar. So it's 26 bar. And if I will check the composition, we have 73 mole percent of hydrogen, then 18 CO2, almost zero carbon monoxide, what we wanted to achieve to produce as much hydrogen as possible. And then we have also other species there. This product stream I'm sending into the splitter, and inside the splitter I'm taking this stream times 4, and then I equally split it into these 4 streams. So all these 4 streams plus this stream are equal, and every this stream I will be sending to different type of carbon capture technology. And again, I will use the cross flow sheet connectors. Now I will go back to the presentation. Here on this slide is the picture where we can select the right technology for us to purify the stream what we produce based on partial pressures of CO2 in the feed and partial pressure of our product. And as we remember, our stream had 380 psi, and the CO2 content was about 0.18. And when we want to calculate the partial pressure of CO2, it gives us about 65 psi. So we are somewhere in here with the partial pressure of CO2 in our feed. So we are, let's say, at the border of different types of technologies. So for our Syngas stream, we can use for CO2 removal the amines. We can use also physical solvents, and we can use also activated potassium. Which technology we will introduce all of the technologies, but let's say you have a project and need to decide. Here is the picture of the comparison of different types of technologies. So you can see how we can purify the streams, and based on your requirements, so which products you want to have and which concentrations and pressures, you can decide between the different technologies. But let's say you want to have the stream with high CO2 purity. From the table, we see that we can use for this amines or cryogenic fractionation. Or if we need a stream with high hydrogen purity, for example, for automotive industry, then you need to use membrane technologies. All right. The first technology, which we will go through together, is a chemical absorption with amines. In this case, the ongoing acid-base reaction between amine, water, and CO2 will be present. So we will use chemistry to pick the CO2. This process works at high and low pressures. So also amines might be used for low pressure carbon capture. And yeah, so amines can get us also to very low levels of CO2 in the treated gas. We are speaking about ppm levels, as we saw in the picture before. So we can treat the gas to the very low levels of CO2. And in general, we have 3 types of amines. We have primary, secondary, and tertiary amines, where the difference is in number of substituents on the nitrogen group. When the amine has only 1 substituent, then it's primary amine. When it has 2, it's secondary. And when it has all 3, it's tertiary. The primary amines are most aggressive compared to the second and tertiary. And usually the substituents are some alkanol groups, so chains containing alcohol groups, since the alcohol group reduce the vapor pressure of the whole molecule, since the better interaction of alcohol inside the water. And this is important when we want to reduce losses of the amine. On this slide, we can see some examples of the amines. So primary one, NEA. Another one is DGA. You can see the alcohol groups are present. So they have better interaction with water and remain with inside water better. Then we have the DEA, which is secondary amine. We have also DIPA. DIPA is secondary amine, as you can see, but here are the two methyl groups with the alcohol groups. So this is the spherical barrier for the other molecules to enter the nitrogen group. So even DIPA is the secondary amine. It behaves like a tertiary. And then the last one is NDEA. So it has three substituents. And each amine has different structure. So also the behavior of the amine is different. In terms of CO2 pickup, corrosion aggressivity, formation of heat stable salts, or vapor pressure, which is important to mitigate the amine losses, as we already mentioned. And since amines are chemical absorbents, here we can see which reactions occurs in the system. It doesn't matter if the amine is primary, secondary, or tertiary. The first reaction occurs in every time. This reaction is very, very slow compared to the others. And here, CO2 reacts directly with water and forms bicarbonate anion and hydrogen cation. Second reaction takes place only in the case of primary and secondary amines, where CO2 reacts directly with amines and forms the carbonate anion and hydrogen cation. This reaction is way faster than the first one, and that's why the tertiary amines are weaker than the primary and secondary, because they react only with this reaction, and the tertiary reacts only with this reaction, and primary and secondary have this faster option as well. And then we have two reactions where hydrogen cation reacts with the amine and forms the bicarbonate anion and forms the cation, and we have the bicarbonate, which also reacts with amine, and those are the products from our first two reactions. So with these two reactions, we are moving the equilibrium more towards the products in this case. So these are all reactions happening there. Then we can have also blends of different amines, and why we would do such a thing. So this way we can combine advantages of different solvents. On the other hand, it's harder to maintain the consistent composition. But for example, we can mix two different amines, amine with piperazine, or the amine with some activators. Based on what we saw, we may have a conclusion like why would we use tertiary amines when they do not perform that well in CO2 pickup compared to primary or secondary amines? And for example, the MDEA, which is the tertiary amine, is popular because it's less aggressive, less corrosive, and so we can use it in higher concentrations. So this lowers the circulation rates and reboiler duty requirements as well. MDA also has lower heat of reaction with CO2, so regeneration is also easier and less energy demand compared to the other amines. For our model, we will use the combination of MDA and piperazine, where we will accommodate the benefits of MDA, and due to piperazine, we will increase the CO2 pickup. Typical concentrations of piperazine move from 1 to 5 weight%, and in this case, it's more difficult to or piperazine has a higher vapor pressure, so we will have a higher losses of piperazine in this case than MDEA. So we need to be careful of that. Now we can move back to Promax. I will find the slide where I was. And yeah, so we are back to the water gas shift flow sheet. And what we are going to do, we want to send our stream to the MDA and piperazine flow sheet. So I'm going to add cross flow sheet connector. You can find it in the shapes inside the streams. And I'm going to click and drag the cross flow sheet connector to my flow sheet. Now Promax asks me where I want to send the stream. I want to send it to MDA piperazine flow sheet. So I'm going to hit OK and go to MDA piperazine flow sheet. In the left down corner, I can see the cross flow sheet connector, so I can just connect it to my absorber. Now we can have a look on thermodynamic package, which we are going to use. So we have the components. I added also piperazine and MDEA to our component list. And if I will have a look, we are using amine sweetening PR and Robinson. And when I will hover over it, I can see that for vapor, we are using Peng-Robinson. For non-specific liquid, again Peng-Robinson. And for aqueous liquid, we are using electrolytic ELR package. Since we have the chemical reactions, and those reactions are taking place in the water, and ionic species are reacting, we need a thermodynamic package which will describe this equilibria between ions inside the water phase. And that's why we are using the electrolytic package for that. This describes it very, very well. I'm hitting OK. Now let's have a look on technology overview. So we have the absorber here when the magic is happening, where we are picking CO2 from gas and absorb it via our amine. I'm going to open. So we are using 45 MDA and 5 piperazine in this case. So it goes to the absorber. In absorber, we want to maintain lower temperature and high pressure since it's favored the absorption. And the rest of the technology, what we see here, is basically for regeneration of the solvent. So we have the rich flush here. Sometimes it's present, sometimes it's not. We have the lean rich heat exchanger to recover some heat from the reboiler and preheat the inlet stream to the stripper. And inside the stripper, we want to have the lower pressure and higher temperature. Then we have the pump. So we are decreasing pressure in this part since we are regenerating our solvent. And then we need to again increase the pressure to the level to be high enough to enter the absorber. And then we want to also maintain the temperature which is on the inlet. And the temperature is roughly the same as the inlet temperature, which is about 48 degrees C. Now we can hop into the column, into the absorber. So this absorber has 20 stages. If I will go to the process data, I can see that the model type was used mass and heat transfer, but usually you can decide either you want to model it as ideal stage or mass and heat transfer. If you model it as ideal stage, it means that every stage or the phase leaving the both phases which leave from certain stage are in equilibrium. In the second mass and heat transfer part, it's not the rule because it's taking mass and heat transfer correlations to calculate it, and this model represents the reality. So if you have in real life 20 trays in your column and you are using mass and heat transfer, you want to put also 20 trays there. If you have 10 meters of packing, also put there 10 meters of packing. Then the important thing is to select mass and heat transfer column type. I have T-suite absorber stripper, and since the CO2 reacts with the amine, this this option, so this one simple click, contains all the kinetics. In Promax, you can select from a very extensive list of the amines, and this T-suite absorber stripper contains all the kinetic data with all the amines available in Promax. All right, so that's the model type. Now we can specify the our column. So I will go to the general tab. You need to specify either diameter or fraction flooding. Let's say we are going to do the design. So I want to have fraction flooding 70%. So I'm enter 70, and I'm going to use this copy to button. Then system factor was already set to 0.8. This represents or taking account some foaming effects. Then we can go to the tray. We specified that those are trays, so we are going to the tray. We have C trays, and since there is the reaction occurring, we need to tell Promax what are the size of each trace. So Promax can calculate how much time the certain liquid stays at certain stage, and from that time and the kinetic data applied, he can calculate how much CO2 reacted and how much CO2 was picked out of the solution, since there is a reaction and the reaction yield was calculated. All right. For the tray spacing, we are going to enter value 0.6 meters. I'm going to copy to bottom again. Wheel height is going to be 7.6 centimeters. This is the default setting, but we can play with it a little more. So for example, first 5 stages will have 60% fraction active area. So I'm going to put 60 to the first 5 stages. This is the 5th stage. And the rest will have only 55%. Also, we can play with number of passes. So for first two stages, we can specify two passes, and for the rest, we can say that we have four passes there. All right, so with this step, we specified the absorber, so I can close it and I can execute this flow sheet. And as we saw, we have the 45 MDEA and 5 piperazine in the circulation, and we can check how the column performed. So I will go to the treated gas stream, open it now. We can see the temperatures, pressures, flow rate, but what interests me is the composition. We can put mass flow, and we can see that we are losing some MDA and some piperazine. And if I will go back to the flow sheet, here is the makeup look. So in real life, time to time, you need to add your solvent there. But since Promax is a steady state simulator, it calculates for us how much certain amine or water we need to add in every time. And that's why this makeup block is here, because we are losing some amine and water there. And if I will go to the mole fraction, we see that we have the most is hydrogen there, then the methane, and we purified the stream to only 0.2%. This is set on a certain way, but with the amine, we can go to very low ppm levels here. So it's up to you how you set the simulation, but amines are powerful enough to clean it to very, very low levels of this CO2 in the stream. We can check also the outlet stream from regenerator to composition. And here, 97% is CO2. Then we can go to the absorber and we can check the plots. So I'm going to the plots, and here we can see the temperature profile inside the column. We can see that the highest temperature is in the bottom of the column, and this is what we exactly wanted to achieve, to have this temperature bulk in the bottom of the column, because here with the here the reaction goes in the most extent, and the rest of the amine is serving for the polishing of our gas entering the bottom of the column. So this is what we want to achieve, have the temperature bulk in the bottom of the column. So that's the absorber. We can have a look into the stripper. Since we have the reboiler there and also condenser there, we have some degrees of freedom. So I will go to the specification, and here inside the specification tab, we can say that we specify the condenser temperature to be 49 degrees C, and we also specify our reboiler duty with lean loading specification. So with this step, we are controlling how much CO2 we want to have in this lean amine, which means lean loading represents how much CO2 is loaded, how much moles of CO2 is loaded per mole of amine. So in this case, we are controlling the level to be 0.17 moles of CO2 per mole of amine. If I will go to lean amine stream, I can go to analysis. I can solve this analysis, and I can see the total acid gas loading per mole of amine is really 0.17. This analysis can be entered anywhere else, so we can go also to the rich amine stream. So open the rich amine, go to analysis, but here there is nothing there, so I can add analysis, and I want to add amine analysis. I'm hitting OK. Yeah, my Promax is thinking now. Okay, so the analysis is added. I'm going to hit solve, and now I see my total acid gas loading is 0.52 in this case, which might be slightly higher. If you will go to Promax Help, you can find the recommended values for rich loadings for the certain amines, because if the amine contains too much CO2, then it's very, very corrosive for our equipment. So here are some rooms for improvement. In this case, we could increase the circulation flow rate, which will lower down our rich loading. And as I mentioned, this is the makeup block, which calculates for us how much water and amine we need to add in every time to maintain the constant flow in the circulation loop. And since we have the circulation loop and it's the closed loop, we have also the recycle block here. And recycle block is basically a solver where it's sitting in here. And in this stream, in like every stream after recycle block is treated as inlet stream. So we need to specify temperature, pressure, flow rate, and composition. And that's our initial guess. So Promax will take the calculation from this point and try to find a solution and iterate towards the solution. All right, so this is it to the amines. We can go to a different type of technology, which is hot potassium. So we basically have very similar type of technology, but instead of amine in our circulation, we will have potassium carbonate there. And with potassium, carbon dioxide reacts, or the potassium carbonate, CO2, and water reacts and forms potassium bicarbonate. And we are going to take account this reaction in this technology. To compare it or to find any differences from amine flow sheet, what we saw before, the main difference is the higher temperature here. So if I will hover over it, we can see that inlet temperature is 130 degrees C. Before it was around 48 degrees C. This one has 86. So we can see that the whole inner system is way hotter than the previous one. Also, the difference is this semi-lean solution. So from downer part of the regenerator, we are taking the semi-lean solution and we are putting it back to the absorber. And with this step, we can save some reboiler duty, but we need to take account for the need of the pump and additional piping. But this is one of the options what might be there as well. And also we have no volatile amines in here, so there are no losses of amines in this case. As always, the most important thing is before every simulation is to check the property package. So I'm going to active environment again. I can check the components, and we can see that we need this molecule in here, but I cannot find it in the my component list there. Why? I will show you a little bit later, but please check that I'm added KOH, there is water, and there is carbon dioxide. So I will explain it in 2 minutes, what's going on in here with the setup. Then to the property package, we have here caustic treating Pang Robinson. I will again hover over it. So vapor and hydrocarbon phase is using Pang Robinson. but aqueous liquid, so our water phase, is using caustic treating. That's the difference from amine sweetening, but only with the name, because this caustic treating is the same electrolytic ELR package as the amine sweetening was using. Just there is one difference, that this caustic treating package is using different viscosity model. So the viscosities are calculated on a different way. But it's the same electrolytic package. I'm going to hit OK. The next difference, so it's basically the same. I need to go to the absorber again. We'll go to process data. We can see that mass and heat transfer was set again. But in this case, we are not using T-suite kinetics, even there is CO2 reacted, because here is the higher temperature. So we are using general mass and heat transfer. And since we are using electrolytic package, the electrolytic package might handle very well also the this type of reaction. I'm going to close it. And now I'm going to show you how we can create this potassium carbonate inside the Promax. So I'm going to draw a stream. When I open the stream, I'm going to specify the temperature, then the pressure, which might be 25 bars, and the flow rate, which doesn't matter which flow rate we will have, let's say 100. And I want to have 27.3 weight percent of potassium carbonate in here. How to specify it? I don't have potassium carbonate there, and I don't know how to specify it. So for this, I'm going to close the window. For this, you can go to shapes again and take the salt example. When you take the salt example, it will ask you which stream you want to specify. We want to specify stream number 4. So stream number 4, hit OK. Now Promax will ask you which salt you want to create. If I will open the drop-down menu, I can see all available salts which you can create inside the Promax in the electrolytic package. But what we want H2CO3, hitting OK, enter the weight fraction, what we want to achieve, which is 27.3 weight percent, hit OK. And with this step, if I will open stream 4, I can see that Promax automatically filled the KOH, the water, and the CO2 for me, because all these 3 species at these certain compositions are forming inside the water 27.3 weight percent of H2CO3. If we want to double check it, I'm going to open stream 4, go to analysis. I will add analysis, and this time I want ionic info analysis. I'm going to hit OK, click on solve, and if I will go to solve composition, in here we can find our salt, where it is. Here it is, and check it that salt mass fraction is 27.13. So we created this salt. Plus, this electrolytic package took all the species available in the stream and creates the combinations of certain salts which might be created, and based on the composition in the streams it will gives you the values how much certain components were created inside your water phase. So this is pretty useful. And we can also go back to our unit and apply this ionic info analysis for example, lean solution stream. So we can go to lean solution stream, open it. I can go to the analysis. I can see that analysis was already added there. Hit solve, go to salt composition, and here we can see what are the salts, what salts were created inside our lean solution. I'm going to close it, and now I will go to Promax help, and I will insert their acids and bases. Acid and bases supported by electrolytic package. So here you can see the all acids which electrolytic package is supporting and all bases. And if you enter certain components there, Promax will automatically create for you every possible salts which can be created, and also ions and cations as you saw in the ionic info analysis. So this way you can check the availability of the components, and Promax usually has your back there and calculates everything for you. All right, that was hot potassium, and now we can move to, so that was hot potassium, and we can check also the physical solvents. So in this case, the CO2 just dissolves in the solvent without any chemical reaction. Physical absorption increases with gas particle pressure, as described by Henry's law. So this process makes sense at higher pressures. Syngas has 30 or 26 bars in our case, which is a higher pressure, so we can use also physical solvents. One of the representatives is DEPG. You can know it under the name coastal AGR or Selexol. Another molecule is NMP, called also Purizol. Then it is methanol, known as Rectisol or Ifpexol. And the last one is propylene carbonate, known as fluor. And all these solvents I showed you is possible to model inside a Promax, and we can have a look how to do that. And this physical solvent, since there is no chemical bond there, it's easier to regenerate. And for regeneration, we can simply use only flashing, for example. We can use also stripping gas, or as we saw in amine unit, we can use reboiler. Or there is also possibility to use some combination of mentioned above. All right, so let's go to DEPG flow sheet, and again we are going to check our property package for this. So those are our components. Property package is Pang Robinson Polar. I'm going to hit OK. If I will open makeup block, I can see that we are using the EPG, so pure solvent in this case. And the difference between the technologies which we saw in NDEA case and T-suite and absorber, because we have no reaction there, and we can check the results, common results, and go to recoveries. If I will go to recoveries, we can say that we can see that for hydrogen we have 98% recovery, and for carbon dioxide 94. This recovery is only for the absorber, but when we want to see the overall recovery of whole flow sheet, we can go to project viewer. We can go to this left side of the window, scroll down, and if I will go to the recoveries, find the DEPG flow rate, the DEPG recoveries, and go to results, I can see here that for hydrogen, we have 99.3% recovery, and for CO2 is 99.9, or it's 93, sorry, 93.82. And when we see the treated gas, we cleaned the gas to 1.44% of CO2. So physical solvents are not that effective in picking the CO2, but depends which pressures you have, what are your pipeline specification. But in most cases, this might be cheaper solution for operation, since you don't need that much reboiler duty to recover your solvent. We can move back to the presentation, and now we can have a look on membrane processes. So membranes are selective barriers which let certain components pass through more than the others. The part of the feed that pass through the membrane is called permeate, and the part that does not pass through is called retentate. The transport of molecules through the membrane is driven by difference in partial pressures over the membrane. So our driving force is the pressure for this separation. And for our Syngas process, both hydrogen and CO2 selective membranes are relevant to use. Which membrane to use depends on the pressure and purity requirements of your product. So permeate will have lower pressures since it needs to go through the membrane, the stream, and the retentates has usually higher pressures, but not that high purities. If we have also other components there, and then two components, what we want to separate. There are also advanced technologies which combine membrane separation with syngas production. So I wanted to show it to you. So we can, as you can see on the picture, we can combine water gas shift with hydrogen separation inside the water gas shift membrane reactor. Or we can also combine reforming or gasification with water gas shift with hydrogen separation in reformer membrane reactor. The same might be applied for CO2. So water gas shift, CO2 in sorption enhanced water gas shift, and all three together in sorption enhanced reformer. So this I found interesting, so I wanted to mention it, but we can go back to the model again. And we can show how to model membranes inside of Promax. It's pretty intuitive, and we can have a look inside the first membrane there. So in process data, you need to put information there as retentate pressure drop, initial permeate pressure, pressure drop, also flow configuration. You have the drop-down list. And if you are not sure what flow configuration might be, for example, you can always hit F1 button on your keyboard and go to Promax Help directly and see the flow configurations. So we have cross flow, concurrent flow, and contocurrent flow. I'm going to close help. So that's what we need to specify. Also, you can select the temperature profile, and what you need to add there is the area of the module. Then another important thing, you need to specify selectivities. I specified the selectivities all before, and how I did it? I did it through permeability constants with GPU. I put the values by myself, but you can also use our references from the patents. So I can show it to you how it was done. So I can click on add. And I made this for all inlet components in our stream. And so we added selectivity number 9. I need to select which component it's going to be. So we can do it for oxygen. You can select the membrane type. Let's use again cellulose acetate. And here are the patents number from which we take the data. You can use them. When you hit enter, it will give you values. You can just put there the values, and with this way, you can specify the selectivity. The selectivity for oxygen is already active, so I don't need to activate any other selectivity. And what I want to show you is that for carbon dioxide in here, we or I also set the upper limit as the constraint limit type. So I put upper limit there, and the upper limit is 2% as the constraint target. So I won't have more than 2% of CO2 in my permeate. With this way, how we specified it, the model count was calculated. So this is basically more the membrane design, that I have the specification, what I want to target, and Promax for me calculates how big membrane I need. Here is the second membrane. It's the same one as the first one, so all the pressure drops, all the selectivities are the same, but there is the only one difference with carbon dioxide, that I don't have the constraint limit type in here, but in process data, since I had degrees of freedom, I need to insert also the module count there. So this is not design anymore, but we can take this as an existing plant, and we want to calculate the performance of this. So as I said, it's pretty intuitive and easy to set up the membrane block, but you need to have the data for it. So I strictly recommend when you are going to work with the membranes in here to speak with your vendor, and your vendor will give you all the data you need. Also, some of our customers, when they have the membrane vendors, they supply them only with results already. So inlet streams and then outlet streams from the membrane. So for this case, they are using the divider blocks. So if you will go to auxiliary objects, you can pick the divider block. It's in here. And inside the divider block, you can specify the fractions what are going to be separated. So this way you can very easily model what's going on in your real technology and then put on it the different other technologies there. All right, so this was the membranes. I can minimize it. And the last technology we have for today is the low temperature distillation. So for low temperature distillation, we can have different configurations based on our target and composition of our inlet stream. Also, when we separate CO2 from hydrogen and hydrocarbons, we need to be aware of dry ice formation. Promax calculates in every moment and every stream block the possibility of dry ice or hydrate formation. And if there are the conditions, it might be formed, the dry ice, then the Promax will immediately warn you. So that's the CO2 solidification part. Then another challenge for this technology might be stream containing ethane with CO2, since ethane forms azeotrope at about 66% of CO2, which means that CO2 is the light key up to 66%, and then it becomes a heavy key. So to perform such a distillation, we need to add an additive which breaks the azeotrope. And this process is also called as Ryan-Holmes process. And we will have a look at this type of process now. For this, I'm going to open a new Promax project. So new Promax, and I'm going to use the pre-built example file. So with every download of Promax, you have the library of different technologies available. So I'm going to hit on open example, hit on OK. And we are looking for Ryan Holmes. Yes, with higher Ryan Holmes system, we can pick the simple one, open it. So I'm using the example file. So every time you are working on a new technology, and you can always go to the example files, try to find if there is something what you are currently working on, because all these examples are based on real technologies. So you can take it as inspiration, like which flow rates were used, what temperatures are there. So yeah. And as you can see, currently I have my old Promax open, and also this new Promax is open. And that is why Promax is not token based. So it means with one license, you can open as many Promax projects, as many instances as you want. So the license is per machine. So only one license for any number of flow sheets I need to calculate. So now let's back to the technology. So in here we have 3 columns. And what I'm going to do, let's check our inlet stream. We have it in English units. So when you open the example files, those are in English units, but you can go always to the options and switch units you want to use. So I'm going to use kilojoule bar. If I will open the stream again, I see that it's already in our European units. So the temperature of the inlet stream is minus 51. So the stream was already pre-cooled before. Then we have slightly higher pressure than we had in our syngas. And let's check also the composition. So in this case, we don't have the hydrogen. We have mainly carbon dioxide, we have methane, and we have also some higher hydrocarbons. For this, I'm going to disconnect this one stream. I will select the blocks I want to calculate, and I will just hit execute block. Why am I doing it? I wanted to show you that the Promax all the time calculates the dry ice formation. So here we can see the warnings that the temperature minus 84 is below dry ice formation, and I can go also to the warnings in here. So it warns me that dry ice might be formed there. So we cannot separate it that easily. That's why we need to add our additives in the system. So I'm going to open the stream, go to composition, and we see that the additives are C5 plus in this case. So we are adding it to the system to lower the temperature down and maintain the dry ice at the dry ice formation. So this is the Ryan-Holmes process, or the system where we are using this kind of additives. I'm going to execute flowsheet one more time. And here you can see that at this point we have no warnings there. So we are not forming any dry ice anymore. If I will go inside the column, we need to again have the condenser and reboiler. So we have 2 degrees of freedom. We need to go to specifications and check which way the column was specified. So here is the first specification. So CO2 in overhead. We have the target there, and Promax calculated the target. And then how much methane we allow in bottoms. We have 0.5. So that's the second specification. So in here we are separating with cold temperature the methane and the rest. In the second column, we are separating CO2 from the rest, so we can check the rich stream, the composition. So mainly is carbon dioxide with some hydrocarbons, and at the bottom we have almost none carbon dioxide, and the rest are the middle and higher hydrocarbons. And in the last column, again, we can check the specifications. So we have IC5 in LPG, we have the limit there, and also for butane, we have the limit in the bottoms. And if I will check the product streams, the composition here is basically the middle part of the hydrocarbons are the most there, and in the bottom what we are using for additives to recirculation are the heavier hydrocarbons. So yeah, and what I wanted to also show you, so Promax didn't give me any warnings, but we can double check it, and we can go to any stream we want. Let's say this residue stream. We can go to analysis, We can add analysis, and we can use this freeze-out hydrate dew point analysis. Click on solve, and this time Promax calculates for us the solid formation temperature. So the solid formation temperature for this stream composition is minus 113 degrees Celsius. If we will go to the properties, we are at minus 72. So it means that we are 41 degrees C above solid formation. So we are in the safe range, because the rule of thumb is to be at least 5 or 10 degrees C higher, and we are 41, so we should be in a very safe region. If we want to also plot it, we can use phase envelope analysis. We can select the dry ice curves. For this, I can hit solve, go to the plots, and here we can see the dry ice formation curve, and here are the stream conditions. This is the conditions inside the stream are not that well, so we can also open different stream for a smoother line and click add analysis. Again, phase envelope, hit OK. Apply also for the curves. Go to the plots, and yeah, the same thing. Here is the dry ice formation curve, and here we are with our stream conditions. When we are in the right side, we are in the safe location. We are not forming hydrates. Where we are closer to the line or in the left, there is the possibility that we can form the dry ice or the hydrates in our system. So thank you very much for your attention.